Alright guys, so in this video, we're going to move from looking at constant velocity motion, so motion where our speed is not changing at all, to motion where our speed is changing at a constant rate over time. And when speed is changing, we say that we have acceleration. So we're going to look at what equations we can get to look at motion where we have acceleration occurring. So before we get into these equations, let's first talk a little bit about acceleration because we've referred to it, but we've never really defined what acceleration is. So acceleration is very simply the change in velocity over the change in time. So just as velocity is change in position over change in time, we can say acceleration A is our change in velocity over our change in time. If we draw this out a little bit, delta, whenever you say delta, it's always going to be final minus initial, when we talk about it in science. So this is the equation for acceleration right here, change in velocity over change in time. Now you notice that I have these little arrows above the V's, and I want you guys to have that in your notes. It's not going to be critically important now, but later on in the course, when we start talking about circular motion, we start talking about these things called vectors, we're going to refer back to this and see why it's important. But the long and short of it is velocity is a vector quantity. When we were doing those motion diagrams and you had the dots to represent velocity, you drew an arrow from one dot to another dot. That arrow had a length and it had a direction to it. Now, what that means is that there's two ways that we could change the arrow. In other words, there's two ways that we could change the velocity which the arrow represents. One way is to make the arrow shorter or longer, which means that we would change the speed. So this is what we usually think of when we think of acceleration. We think of speeding up or we think of slowing down. But in the second quarter, we're going to talk about motion where our speed might be constant. Say we're moving in a circle at a constant speed, but we're constantly changing direction. And it turns out that if you change the direction you're traveling, you're changing your velocity as well. And because you change your velocity, you're accelerating. So another way that we can accelerate is when we change direction. So in your car, you could accelerate by hitting the brake or hitting the gas pedal, or you can accelerate by turning your steering wheel. Okay, so that's what acceleration is. Now, what we want to do next is want to get equations that allow us to find the distance we've traveled, or maybe a velocity, the final velocity we're at, or the time we've traveled, or even the acceleration that we experienced if given a situation where we are accelerating. And for that, we need equations. So rather than just show you these equations and be done with it, I want you guys to have an appreciation for the fact that these equations come from somewhere. We don't just make up these things. Okay, so this is going to get a little mathy, but I still want to show it to you. So to get to the acceleration part, I first want to show you this velocity versus time graph when we have a constant velocity. So in other words, our velocity is going to be the same the whole time. It's going to have some value v. Okay, and it's going to travel for a certain amount of time, t, down here. Okay, now notice that the area under this line is going to be, it's just a rectangle. So it's going to have a width equal to time. It's going to have a height equal to velocity. So the area is just velocity times time. And you guys should recognize, oh, velocity times time, that's just distance. Okay, so that's the distance that we've traveled. And it turns out that this applies to all velocity versus time graph, where the area, this area under the curve, is going to be equal to the distance that you traveled. Okay, so it doesn't matter whether it's a straight line, it doesn't matter whether it's a curvy line. If you can find the area under the curve, you can get the distance. And if you guys are in calculus, you're going to learn about these things called integrals. And integrals allow you to get this area under curvy graphs. In fact, calculus was made to do physics. Physics is kind of easier if you do it with calculus. Of course, the caveat is you first have to understand calculus, which is kind of a big hurdle. But for right now, just keep in mind that the area under a velocity versus time graph gives you the distance that you've traveled. So this is a graph for constant velocity. Let's look at a graph where maybe we don't have a constant velocity. Maybe we have a constant acceleration instead. So instead of starting at 0, just to make things a little bit more interesting, let's start off. So this little 0 is initial. So this is going to, maybe we'll have a starting velocity for this case. And this whole axis will be velocity, this whole axis will be time, and we're going to end up at some final velocity. And so because we have a constant acceleration, this is going to have a slope. Let's say it's a positive acceleration. So it's going to go up, and it's going to have a slope, and it's going to increase my velocity until I hit some final velocity. And as I said in the last slide, if I can get the area under this curve, I can get the distance that we traveled. And so we can look at this area as kind of two shapes on top of each other. One is a rectangle, okay? And so this rectangle will have an area of v naught, the height, times the time I traveled. And then this triangle right here, this height, from there to right there, is going to be VF minus my initial. Okay, so that's just this height, just this line right here. And then its base is going to be time. And so when I look at the area under the graph, I'll say that it's going to be the triangle area, which is 1/2 base. Okay, so times height, VF minus V naught, plus the rectangle area, which is V naught times T. Okay, so that looks pretty intense. Let's distribute the time, so let's multiply through by time. And I'll get 1/2 VF times T minus 1/2 V naught times T plus V naught times T. Okay, and that we can simplify this. Okay, so I'm going to move down here. A little bit more space. I can combine this, I can combine this, and I'm going to get a I'm going to get a positive 1/2 V naught T. So this just turns into 1/2 VFT plus 1/2 V naught T. And if I factor out the 1/2 and I factor out the T, I'll be left with this equation, 1/2 T VF plus V naught. And as I said, this is my area, this is my distance. So I'm going to simplify that with delta x. And this is the distance that I've traveled. So now, if we have acceleration, instead of having the distance just be velocity times time, it's now going to be 1/2 time times the sum of my initial and final velocity. So it's a little bit different equation. It's not a hard equation, but it is a different equation. Okay. If we just kind of very quickly look at position versus time graph for acceleration, I'm not going to go nearly as much into the derivation of this one, but say this is x times time, right? What you would see is a parabola. So we would always have a changing slope because we always have a change in velocity. And so for this one, it turns out that the change in position that occurs, now we're not going to look at area here because this is position versus time, but the change in position that occurs, this y, is some sort of parabola. And, just not to spoil it to you guys, but I would take my initial velocity times the time plus 1/2 my acceleration times time squared. The squared right here is how we get the parabola. So this equation will allow us to find our change in position if we know the acceleration and the time and our initial velocity. Okay, so that's just two of the equations. And then you can sub them into each other and you can derive two other equations. And so this is the slide. These are called the kinematic equations. I want you guys to write these down in your notes. The x that you see here, okay, that stands for position. Anytime you see a t, that stands for how much time has passed. Anytime you see a v, that's velocity. And anytime you see an a, that's your acceleration. Okay, so we'll be working with these equations a lot in this course and for the rest of the quarter for sure, and we're going to be using them honestly pretty much through the rest of the year. I want to make it very clear, you guys do not have to memorize these. You will always be given these four equations. Now you're going to probably use them so much that you're going to end up remembering them, but you don't have to remember them. Okay, but I do want you to have them in your notes so you can refer to them. We will practice a lot in class as far as how we can use these to solve problems and the different types of motion that we can use these for. So this is your introduction to kinematics. I'm pretty excited. I'm not sure if you guys are excited, but I'm pretty excited because these are, you can do a lot of fun stuff with these. So anyway, get these equations down. We'll do some activities and practice problems in class, and we'll get you guys being experts in using these.